Let's see. Yes, we are recording. Correct. Perfect. So it's a good time for us to actually go over a previous exam so that we know exactly what we are expecting for the midterms. And this is your fall 2023 paper, which is 1 year, just 1 year back. We do tend to repeat problems, but it's not exactly that this problem is going to appear for your exam. The functions of these variables or the functions might actually be different. Now, you need to, first of all, from just the PDF that you have out here in front of your screen, from just that PDF, you should be able to actually infer two things. One is that this is PDF, and we are needing to find maybe the CDF or maybe some other things from here, right? And you actually can find out the region of operation, which is called the region of interest. Now, region of interest also existed when you started with function of one random variable or just one random variable, because this is like just the operating zone for the function, right? So every function has a specific domain of operation and a specific range of operation, right? These are all set theory. So from that perspective, you have this particular function operating from 0 to 2 from x-axis and 0 to 2 from y-axis. So it's like a square, right? So we are going to actually, again, I'm going to try and shift to the doccam mode. I know it's an inverted zone, but what we are trying to do is basically learn how to work it out step by step. I'm going to call it out so that you can basically understand my voice and somehow follow my inverted picture if it's any use. All right. So first of all, finding the value of k, you know that we already have a formula for even when you're working on one domain, just when the value is like x, there is no y there, right? So you know that if you integrate the entire PDF, you are going to basically have 1. So you know how to solve the value of k for one variable. Now you're going to do it for two variables. What is the difference? Instead of one integration, you have two integrations to solve, right? So you do it one after the other. You solve the inner integration first, and then you go for the outer integration, and then you actually solve the value of k, right? And then you go on to the joint CDF. Joint CDF, when you find out CDF, I think there were 3 students out of all the 50 students that we have in the class that actually forgot that the upper limits of integration for the CDF is not these values. The upper limits will be x and y. The lower limits will be 0 and 0. So we are going to actually, again, I'm not going to work out the entire integration problem, but I'm going to give you some hints on how you can work it out. You can also use your calculators if your calculators have the values or equations in x and y, capability of giving you that equation in x and y. Marginal PDF and marginal CDF is a very, very powerful tool because this is a joint criteria. It's sometimes interesting for us to see how one variable is reacting in order of this entire function. So for example, if only we have to find out how x is reacting to this entire function change, how only y is reacting, how do you find that out? Basically, you integrate out the terms of y when you're trying to find out x, and you integrate out the terms of x in order to find out y, and we are going to see. So these three is it's kind of simple, because we are going to solve a couple of problems in the again. I'm going to try and see if the docam works or not. But when it comes to these kind of problem, x lesser than y or x lesser than x is y lesser than x is, I'm sorry, x lesser than y or y lesser than x square, the sketching part kind of becomes a little bit difficult because quite often students don't exactly catch that, okay, this is a parabola, or oh, this is like a straight line. And not only that, you have to basically also know the zone of operation, right? Because the zone of region of interest is out here, right? And then you have to find out the correlation and covariance. Now, this problem, if you know how to solve this problem, this is a full score. But the only challenge in this problem is the time required for you to solve this problem. So you need to make sure that you know exactly what you are doing when you say this or correlation, covariance, and all those things. And then this part, I don't think Dr. D has covered, and I'll give you a very I don't think I think I've mentioned only once or maybe not none. So don't be very concentrated on part F, but I'll give you the tricks and tips of how to actually determine if it is independent, orthogonal, or uncorrelated. Okay, so there's a very simple way of doing that, right? In case it comes up, all right. Now let's move on to the second problem. So this problem, I would, if I were a student, I would ideally keep a good 20 minutes to solve this problem, even more, right? So in a 1.5 hours of exam, say for example, 20 minutes of your time should go into this particular problem because it requires that amount of intricacies of solving the problem. The second problem is a transformation. I don't think this is covered in your syllabus. Nevertheless, I'm going to, if I find time, actually talk a little bit about this if there is time again. Now, this is also a very, very important problem because this is function of one random variable, and this is exactly where we are going to start our entire topic. Now, this problem has been repeated a lot of times, so you might get a different function out here. Nevertheless, whatever function you get out here, it's e to the power of x, u to the power of x, a to the power of x, something, just a straight line equation, doesn't matter. The solution, the path of the solution is still the same. Okay. So function is not important. How you solve the problem is actually important. Okay. So we are going to actually cover this, and we are going to start with this, in fact. Okay. Now this one is a little bit complicated. We usually do not go into this kind of domain again because we did not cover this kind of problems, right? So I'm going to actually do another problem instead. And if again we get time, we are going to touch base on this one. By the way, this problem is not that difficult. It's just that x and y are independent, and x is a zero mean unit Gaussian random variable. Y is also a unit Gaussian random variable. And what we are trying to find out is that expected value of a certain type of function of x and y. So it's not very complicated. It's just that we have to directly put it into the formula. But we have a range of that formula as well, 0 to 3. So we have to just put it into the equation. So we are going to see step by step of how to actually do it. But again, this I rather would actually cover how to do it than this specific problem in itself. And then we have, so this was a absolute random thought from Dr. D. Okay. So last time he basically wanted to ask theory questions. Okay. So don't be very boggled if you see theory questions, because it's actually very simple to answer, and it's actually scoring. A lot of people scored 10 out of 10 points even if they did not solve the problems correctly. So A is, what is the definition of random variable, right? So you don't have to write a bookish definition. You can be just giving me an example of it, or Dr. D, right? In this case, it's Dr. D who is actually going through the exams. So you can just give him a random example, as many examples as possible, right? The axioms of probability is basically from the first exam. So that was a curveball for a lot of people because they forgot the axioms. The definition of CDF, you can just write fx of x. Again, it's not specified that this is a single random variable or multiple random variable. CDF and PDF formulas will be given at the back of your exams. You can literally just copy paste this definition from the back and write a couple of lines saying that CDF is basically cumulative distribution function, blah, blah, blah. Write down one equation of two independent random variable. We are going to go through the independent random variable in a minute. So we are going to be able to see what's that about. And then we are going to write down the equation for correlation coefficient. The funny part about this is that if you just go to the back of your exam, which is this part, the formulas are literally out here. So students got confused and they could not answer the question. You can see that I have put down all the formulas of CDF, all the formulas of PDF. You scroll a little bit down, the entire formula for the expected value, the entire formulas for the covariance, and finally your correlation coefficient. So you just had to basically copy paste it. So if you get a curveball, do not panic. There might be answers in the answer sheet itself, and you just have to basically consult it. All right. So that's the content. I'm going to switch over to my docam, even though it's inverted. I'm going to call it out so that you can actually try and solve it along with me. So the first problem that we are going to tackle is this problem. Okay. So we are going to start from here, all right? And we are going to build up our story because we have to understand the intricacies of the region of interest. And to understand that, we basically need to again start analyzing on where we actually lie with the region of interest. Okay. So here we go back to the screen again. This is an inverted thing, so I'm sorry about that. For those of you who are watching this online, please follow my voice so that we actually can solve the problems together. So first of all, let's actually go to your homework 4. So your homework 4 is all about the last portions of your, wherever you left exam 1, the last portions of that. So you should be able to have a lot of practice on how to calculate the expected value or the variance or the, all the other fun stuff like that. And basically, what you are going to do with this fourth homework is just practice. Now, entropy is also going to be an important concept, and we are going to talk about that through your homework 4. But I am going to actually just do one specific problem from homework 4, which is basically 491. And it's not that that's my favorite problem to solve. It's actually easier for me to explain that problem to you. Okay. So follow my voice, even if you are seeing an inverted whatever. I wish I could actually correct it. I actually can try. Let me see. Let me see if I can get help. Hang on. The camera is coming in front and I cannot see it. Most of the people know who I am. Yeah, it's fine. You are there, you remove. Okay. So this camera is like, I don't know how to, like, if you can see, like, it's completely like, if I switch over, you can see that this is inverted.
Oh, it's mirrored. Okay.
Yeah. How do I fix it?
Go to more. See if that does anything.
More? Okay.
Yeah. Recording and transcribe. Maybe? No.
No, I have to stop record. Dude, this is on recording.
Video effects and settings.
Okay.
Settings. Top.
Oh, okay.
Mirror my video. Have off.
Why would you do that? Oh my God! Thank you so much. Perfect. Thank you. All right, we're back. Yay! Yes, yes, please. All right. So now let's actually do the entire video. So pay attention to this one because this one is going to be important. Okay. So we have a problem. This is 491. And we have a problem y equals e raised to x. First of all, y is a random variable. X is also a random variable. Okay. Let me actually go back to my screen and see if y'all can see anything. Shout out if you cannot, because this is going to be important. Yeah. Let's actually, yeah, can I zoom in? No, yes. Well, you have to do with what we have now. Let's see if I can decrease the opacity. Okay, that's better. Anyway, so we are back to our problems. Okay, so what is the general ask of this problem? The general ask of this problem is always to get to the PDF. Okay, so please be sure on what is being asked. Is it the PDF? Is it the CDF? What is being asked? Okay, so if PDF is a question mark, then you have to do a little bit more calculations. So where do we exactly start this problem? You have a random variable, you have another random variable. Basically, this is a function. So if you were younger, much more younger, you would have actually studied a function like this, right? And this would have been a positive exponent, right? So the positive exponent is not really interesting, but when we actually talk about random variable, this value is variating with this value. That's all it means. So this is just another function. Use capital letters to indicate random variables. Please do not use small letters, then Dr. D is going to be very unhappy. I might actually, sometimes, students make mistakes and I'm like, okay, yeah, they meant this. But then, let's try and make sure that we don't make mistakes like that. Now, the region of operation is also important. So we are going to start with that. So somehow this problem did not specify. Let me actually just make sure that I am going over the same set of problems. I don't think this problem has actually specified a specific region of interest, but for all purpose, let's take the region of interest to be greater than 0. Okay. Your exams will be having very specific regions of interest. Okay. So this one we are taking such that y is less than 0. So imagine that I'm using a small y out here. Okay. So small y out here, y. Okay. Why is it small y and why is this a capital Y, right? So there's a reason for that. So to go into the depth of this problem, how do you tackle these kind of problems? There are various approaches of tackling this problem. First of all, we are going to actually, usually at the university level, we concentrate on one very typical approach of solving it. Again, there are multiple approaches of solving this. Okay. One of the approaches to actually go for finding the CDF first. Okay. CDF is basically, if once you get hold of the CDF, you can always differentiate the CDF to get PDF. Okay. PDF, you can actually go about finding the PDF, but it's much simpler for us to basically find the area that the curve encloses, right? So what is the definition of CDF? Again, one of the questions for your sample exam that we have viewed is what is CDF? So if I were you as an examinee, I would actually go back to the definition of, whatever is there at the back of your exam. And I would find that this is P of capital Y, okay? So if I'm defining Fy of Y, how is it? P of Y less than small y, right? This is the definition. Now, what does it exactly mean? It means that this value, whatever value is there, whatever function is there in this specific. So if y was a straight line, which has mx plus c kind of equation, then that particular thing would variate as a straight line. If this would have been an exponent, it varies as an exponent. If this would have been a parabola, it varies as a parabola. Doesn't matter. The basic point is that whatever functions you have, that value is going to actually go about, and then there is a specific value which is called y, and your CDF is defined until that y, right? So now, what can you do in order for you to actually try to find out what does the area look like, right? So you have to first of all find out the graph, right? So what kind of graph are we dealing with? Or what kind of plot are we dealing with? What kind of value expansions are we dealing with? It's an exponent. So then we substitute y out here. Now this substitution method that we are actually working with, this is one of the ways, again, one of the approaches of solving the problem. So the substitution method works on the way that, well, we have to kind of try to find out, you have to pretend that you almost know this specific random variable. So there will be a change of random variable from the approach where we are taking y to the approach where we are going towards x. We don't know either of them, but we are going to see how we can actually try and solve that. Okay. And this is a very realistic approach because neither of the random variables are known to us. Sometimes you'll be given, and I'll give you applications of it. So don't worry if you are confused about why are we moving towards the random variable x from y, because y is an unknown. Well, that's a random variable that we have established in the very beginning. x is also a random variable, right? So both are unknown. So why are we actually moving towards the towards x? So out here from this stage, the only thing that you can do is to take everything in terms of x. So if you do that, if you like, you don't have to agree with me at this point. If you do that, then what does it look like? So this is an exponent. If you inverse that, what happens? You get ln of y, right? So if you don't know this, some people actually basically remember this or memorize this. Basically, this is an exponent, right? So it's log of e of whatever value. So if you take a log of e on both sides, log of e is also called ln, right? So this log of e kind of log of e of x, which is x, and log of e of y, which is ln of y, right? Basic logarithmic substitution, right? So this again looks like the definition of the some sort of, because this is a value. So let's actually expand on, first of all, what are the parts. So when you write this equation, this is the random variable, and this is just a random value, the value on the entire x-axis, y-axis, wherever it is. So this is just a value, and this is the random variable that we are dealing with. So hence, we can write this as a CDF of x right now, because this definition kind of goes towards the definition of x rather than y, right? Now, what do we put inside the bracket? That's an interesting question. So if you go back to the definition of fy of y, you see that the small variable that we are using is what we are having on the right hand side of this entire inequality, right? So whatever we have on the right hand side of the inequality, we write it inside the bracket. Make sense? Why do we do that? Well, it's to indicate that this particular variable is going to vary it until this value is reached, and that's going to be your CDF, right? Whatever the curve is. Once you reach this point, this kind of logical explanation of transforming the CDF of y in terms of the CDF of x, okay, you can basically say that, well, we don't have either of the values, so fy of y is for me fx of ln of y for y greater than 0. That's the basic definition of the CDF of y. Okay. What about the PDF of y? Okay. Now the PDF, as you know, is a differentiation of the CDF. So what we do is we do ddy of fy of y. Again, we have to find out the PDF of y, not x. So that's why we differentiate by y, not x. So here is where you have to remember the chain rule a little bit, all right? And by that you mean ddy of fx of ln of y. Why? Because that's the fy of y, just substitution, right? Now from here, what can you do? We have to differentiate it. So what kind of differentiation are we looking at? We don't know fx of x, right? So, or fx of this. We don't know anything about this specific function. Well, yeah, that's already given that we do not know it. So we just write f dash x of ln of y, right? Now, chain rule, first you differentiate the outside, then you come to the inside, because this variable is also a variable in y. Outside differentiated, come inside, and we are going to sit with a value which is going to be a differentiation of first the outside, and then you have multiplied by dy of ln of y. Agree? So that's the chain rule. So you have to remember this, that if you have another variable which is the same differentiation power, and there's a function outside, or there's another variable parameters outside, you actually first differentiate that and then move it. So this is basically 1 by y fx of ln of y. And if you don't have the tables, this is easy for me to actually do it because I've done it maybe 1,000 times. But if you don't remember this, then you might actually be a little bit of trouble. So I would say that I do give the integration and differentiation table. I will try to give that, and I'll try to convince Dr. D to do that. Just in case it doesn't happen, look over or glance over your basic, differentiation, like e to the power of x, ln of y, x, or x to the power of n, a to the power of n. All these are maybe a cos or a sine and a tan. All these are very common, right? So you should be actually able to memorize these couple of things, and you'll be good. Right? So now the part B of this is a little bit interesting. So I'm going to actually go back to the book rather, because I want to see what the part B is all about. Let's see. So let's see. Where is my book? So for this is chapter 4, I guess. Okay. So again, if this kind of problem comes up, you have multiple approaches of solving them, and internet might give you actually quite a lot of approaches. This is one of the approach that is approved, and it's covered in multiple other schools as well. So we are sticking to that. If you don't like this approach, you can solve it by other means as well, no problem. So the part 2 says that find the PDF of y when x is a Gaussian. Now finally, we actually have something to actually work with. So the part B is when x is a Gaussian. Now the funny thing about a Gaussian for x is that whatever you do with x, y will also be a Gaussian, no matter what you do. Okay, you scale it up, you subtract, you divide, you add, whatever you do. So y is also a Gaussian at this point of time. So in case y is to be a log normal random variable, so don't get distracted by fancy words. Basically, you just have to find out the PDF of y when x is Gaussian. Okay. And then there's a plotting thing going on. I don't think we are going to actually give you any plotting questions. If you do get a plotting question, you can definitely see the nature of a Gaussian, and you know that the Gaussian is some kind of a bell-shaped curve, right? So that's not going to be too much of a problem. But how to solve them? So how to actually go about solving this problem is that, now remember, x is a Gaussian out here, but it can be any random variable. So I can take x to be a really random variable, a Riccian random variable, anything. So in that case, what do you do? First of all, concentrate on the fact that you have the value of x. Okay, you have to start with x. So x is Gaussian. So what does fx of x look like? Okay, so this will be probably given at the back of your exam as well. But then over the top of my head, x minus m whole square by 2 sigma square divided by square root of 2 pi sigma. If I'm not very wrong. If I'm wrong, please don't quote me. So this is the value, the PDF of, so this is the PDF of x when x is Gaussian. All right. So now from this PDF, you have to find out the PDF of y. But wait. Okay. Wait. We have, so we already have fx of, I'm sorry, fy of y given as this, right? Why do we have that? So we'll recollect a little bit. We are going slow out here. So when you differentiate the PDF with the CDF, this is the capital F. So this is CDF. So when you differentiate the CDF, you get PDF, right? So we are trying to find out this guy, right? So this one is basically the PDF, 1 over y fx dashed or fx bar or fx prime of ln y. So this particular part is already the PDF. So my already existing PDF is this. Now we are told that x out here that we are trying to differentiate and whatnot is basically a Gaussian. Okay. So what do you do after that? We try to find out, well, if x is that, then what does y look like, right? If x is a Gaussian, so I'm just going to write this down again, over square root of 2 pi sigma, and we have fy of y equals 1 over y fx of ln of y. All right, cool. So we have this. This is already there, given, right? Then if this particular PDF, so this is, remember, this is PDF of x. What we are trying to find out is the PDF of y. All right, we are trying to find this out. So let's try it with the PDF of y, which is 1 over y. All right, that part is not going to change even if the PDF of x is like that, right? What can change, however, is that this is already a PDF, right? The f, so when you differentiate the CDF, this is already the PDF. So what is interesting about this PDF is the variable inside the brackets that is sitting out here, right? So instead of x, we have ln of y, right? Had this been a normal, like fx of x, then whatever we have as the function or of the PDF out here would have straightway come and sit out here, because f prime of anything is basically the PDF itself, right? So this one is the CDF. You differentiate the CDF, you get the PDF, right? So whatever is sitting inside the bracket is now going to be utilized to actually find out the value of PDF of y. How do you do that? So just substitute the x with ln of y minus m whole squared by 2 sigma squared over square root of 2 pi sigma. How many of you have understood completely this substitution? If there is unanimous no response, I am going to probably move on to the next sections from here, because there is a very similar problem uh, in functions of two random variables, which is there in homework 5. In fact, I think that's the last problem that you are going to solve. And that also is going to work on this similar premise. I'm not saying that's the similar problem, but it's going to work on the similar premise. All right. So once this is complete, we can actually safely say that for any random variables now that you have any of them, like this one is just one example of random variable. So you can have x as Gaussian, x as anything, any other random variable. So any of the random variables that you have, this is the same process. First, you find out the CDF, because it's easier for us to actually basically get hold of the curve first of all, before you find out the area under the curve and all those other things. So this is the substitution method. There are other methods of solving it, but this is the much more easier way of doing it. Okay. So once you actually get over this, so you'll actually find a couple of practice problems in your homework 4 as well. Like you can practice 480, for example. You can practice, let's see what else is there. 477 as well. So 477, I've given you a Rayleigh random variable, for example. Same thing, it's maybe a function of x, right? So if there is a possibility of plotting, please plot it. If you don't know how to plot it or don't want to plot it, that's absolutely fine. But then do not go wrong in the functions. So you can practice 477 and 480 rather. You can also practice 485. So practice 477, 480 and 485 along with 491. So this should cover functions of one random variable. Okay, and this is going to be there for the exam. I don't know which type of random variable is going to be there, but it's basically working in the same premise. Once you understand the method, it's step 1, step 2, step 3, step 4. So if I have to divide this into steps, what would I do? Let's see. So step one is to actually recognize what is given and then what you want to get to. Step one would be, first of all, trying to find out in this problem, trying to find out the CDF. This one would be step one. All right. Step two would be to, after you find out the CDF, make the substitution. Okay. So step two will be, once you actually find out that Fy of y, then you have to actually turn this. In fact, this one will be step two, that once you actually find out, the first step is to find out that you need the CDF. The second stage is, once you need the CDF, you have to change the variables from y to the x. So that's step two. And this is probably the step three. That is the differentiation. All right. So these are the three steps involved, and you are going to basically get the problem correct. Now, if there are any specific random variables discussed, that, okay, this is a Gaussian, what is going to be the final thing? Then if whatever is there inside the brackets for f dashed x or f prime of x, whatever is there inside the bracket for Rayleigh random variable, Rician random variable, whatever types of random variable, wherever you have x, just substitute that with whatever is there inside the bracket, and you are going to arrive at the PDF. Barring obviously you put all the other factors like 1 by y and all those things correctly, you are going to basically arrive at this particular equation. So similarly, we are going to move on. All right. Moving on to a little bit of a bigger problem, right? So I'm going to solve 526, although probably it's done in the class multiple times, but we are going to actually take it step by step because this is the big problem that we are talking about, which kind of contains 40 points. All right. So I might not have given you the solution for part E. I apologize. I probably will have to upload the solutions again, but I'll give you the answer out here. So yeah. So the second problem that we are trying to solve is, this is the two random variable zones. Okay. So the two random variables, actually, for two random variables, remember this, that we have a region of interest. Okay. Now, don't we have region of interests in function of one random variable? Yes, we do. But we are actually are not too much concerned about it. But I did actually give you a small hint in this specific problem where you can actually see that this entire operation will be done only when y is greater than 0. So that specific operation is that region of interest. Why is region of interest so important is because that is basically going to determine the limits of integration for CDF and any other expected values and all those other things that you have to find out after this. So all the limits of integrations that you have is basically going to be determined by the region of interest. Now, why is the region of interest so important is because when you are operating in a certain zone, right? When you are bound by certain zone, you have to like, for example, if I draw a circle and if I say students have to remain inside the circle, if the students go outside, they are basically I know, maybe they have to, get removed from the game or something, whatever. So this is almost like that you are operating within that zone of interest. Okay. Outside that zone of interest, whatever the function is doing, we are not interested in it. And this kind of focus on a specific zone is important for us. Actually, it is one of my primary part of my research as well, that we are focusing on a certain zone because the function might be like, it might be ever expansive. So we are trying to basically isolate that specific zone and try to study what type of function we have in that specific zone. That's why the region of interest is important. All right. So how do you find it out? How do you find out the region of interest? Or, I mean, first of all, let us take the problem down. So what the problem actually states is that if fxy of xy, so now we have shifted from fx of x to fxy xy. So this is the random variable out here. These are capital letters, and these are the variating parameters. So they are in small letters. And I'm just going to take a very simple one. right, out here. Obviously, this function might be a little bit more complicated. The more complicated it is, don't get scared. It's just going to take you more time to actually integrate this entire thing. So do not panic if the time is getting over. Sit with this problem and try to finish this problem off at the very beginning of the exam. Because if you keep this from the end and say that, okay, I'll solve all the other problems and then get back to this, what is going to happen is you're going to lose time. Because the other problems you have, I mean, it takes reasonably 10 to 15 minutes for us to actually get through them, but this one will take you time, so sit with this. Okay. So the region of interest again is determined by some sort of bounds. Okay, so the bounds on this particular function is this: 0 less than x less than 1, 0 less than y less than 1. So what does it mean though? So, well, I mean, technically speaking, if you are to operate this within, like, just forget the function. If you were to see that x is varying from 0 to 1 and y is also varying from 0 to 1, you know that this is a square, right? This is just a square and nothing else. So, well, I mean, you don't even have to think about it. That's the point of it. But anyway, how do you put this in equation, or what do you do with it, right? So first of all, the first question is to find out k. All right, so find k. That's part A. So this is important. This is important because, not because that it's like um you know it's hard or something like that, but the value of k is going to determine all the other parts. So most of you have lost points in the exam one because you have not paid attention to the value of k, or how to solve the value of k. So pay attention to that, okay? All right. So now what we have is, okay, let's see how this works. All right. Oh, no, it's not going to work this way. All right, so find the value of k. First of all, you know the formula for dealing with a single integration. Had this been a single integration, all right, I'm going to just space it out, okay? Had this been a single integration, you would have said this, right? So whatever the function bounds are, right? So I'll write the generalized function bounds. The generalized function bounds are minus infinity to infinity. Fx of x dx is equals 1. Where did we find this? We found this in our first property of one random variable in chapter 4 at the very beginning. This is one of the properties of PDF, that if you integrate that without any bounds, that is minus infinity to infinity, the area under the curve is always going to be 1. And we have more successfully learned this. Now what we are trying to add to is another variable, right? So if there's another variable, there's also going to be another integration parameter. And this is what we are trying to do. So for this problem, how does it change? So the first change that we have is the integration limits, right? I hope you can basically see it. So the integration limits now is from 0 to 1, okay? 0 to 1. Where did we get this from? We got this from the region of interest that we have out here, okay? So 0 to 1 is for x, 0 to 1 is for y. What function are we trying to solve? We are trying to solve k x plus y dx dy equals 1. All right, this is the step 1. Correctly interpret and write the limits of integration, the function, both the differentiating parameters, and that it equals 1. 4 parts to this problem. Go wrong in any of them, you lose points. So then your step 2 is basically integrating the entire thing. I'm not going to go into too much of details of it. You have this in the solution. But first, what you do is you tackle this problem one at a time, right? You first of all have an addition. You can separate the addition out, right? So you can basically take the k outside the bracket and x plus y, right? So x is going to be one parameter, y is going to be another parameter. You can do that way, or you can basically take x, y as one set of one set like x plus y, and then differentiate that. If you choose to do that, then first you can start with the value of x, and then you can go on to the value of y. You can start with y, go on to the value of x, so and so forth. So if you start with the value of x, let's see what happens. Let's see. This is from 0 to 1. That means this is y is from 0 to 1. So I'm differentiating x. So this is x squared by 2, x squared by 2 plus xy, but that's from 0 to 1. So x squared by 2. So this is half. I'm just trying to, work it out on my own. And xy. So this is y, okay, dy. All right. That's equals 1. And then you can actually also differentiate, I'm so sorry, integrate y and then find out the value of k, right? So I'm going to give you the value of k is basically just 1. That's your step 3. Okay. Usually in my rubrics, I usually go from step 1 to basically, oh, sorry, I'm so sorry, this is step 2. Step 1 and step 2. So once your step 1 is correct, if you have 5 points to this one, my rubrics would read 5, that means 4 plus 1. Okay. Dr. D's matrix might read a little bit different. So you have to be now not only careful about writing the steps properly, we have to also be careful about solving the problems. Because depending on the value of k, your entire problem foundational base is this one. So please try and calculate this particular integral with time. All right, moving on. Once you find out the value of k, we can substitute it. But we'll move on to the next part of the problem. That is part B. Part B is to find out the CDF of f x y x y. Okay. So CDF definition, by definition, what kind of definition does both of these variables have? You have x less than x, comma y less than y. That's the definition. Okay. So what does this mean though? That means that we have double integrations, x less than small x, y less than small y. So whatever the lower bounds is, okay. So in general, the definition is from minus infinity to infinity, f of xy, oops, sorry, dx, dy, okay. But is it minus infinity to infinity? Is this the correct definition? No, this is not the correct definition. This should be x and this should be y. This is the most major mistake. I have been correcting at least, I don't know, over 1,000 exams. Trust me, out of those 1,000 exams, at least 400 to 500 people, or maybe half of the people, have gone wrong in putting minus infinity to infinity. Please remember that CDF is still a specific bound. So this function is going to be a function in x and y. And that's absolutely fine. CDF is not a value. So people have substituted the limits of integration, which is 0 to 1, right? And they have actually found out a value. So if this is coming out to be 4.793, no, incorrect. This is an equation in x and y. Okay. So taking that into consideration, the lower limits of integration should be considered because that is the region of interest operation. So this is the region of interest, right? This is also the region of interest lower bound, right? This is also the region of interest lower bound, right? The upper bound is still x and is y, okay? And since k is 1, so we have x plus y dx dy. Once you reach this stage, this one is step 1. Writing this entire thing correctly. Now you have to start integrating, which is step 2. So again, it's the same thing. If you integrate this, what will happen? So first of all, I'm taking and integrating out the The x, it's the same thing, x squared by 2 plus xy, we have dy, and the integration limits is from 0 to y. So again, if you differentiate that, I'm just going to give you the final response of this one, x plus y by 2. Okay. So again, if this would have been my rubrics for all x between 0 to 1, y between 0 to 1. Okay. So is this essential? So some people actually tell me, is this essential? Yes, this is essential in terms of the region of interest. Whenever you come up with the PDF and CDF equation, please also mention the region of interest of operation of this entire specific problem. Points will not be deducted, but this is a good way of, good practice of actually learning this entire thing. So once you come to the CDF of it, people will often actually start asking you marginal PDFs or marginal CDF or something like that. So what if you start with a CDF, right? If you start with a CDF, this was clearly starting with a PDF, but because this is small f of xy, but then if you start with a CDF as well, you can basically differentiate that to get the PDF and marginal PDFs as well. So the part C is basically marginal. And again, this is going to be step 2 for this one. So again, if finding the CDF is a 5-point problem, for my rubrics, it would have been 3 plus 2. So now I'm going to be actually careful on the value of this particular equation, because I want to not only know whether you know integration or not, that you have actually understood on how to basically substitute and how to basically find out whether this is an equation in x and y or this is just a value. If it's a value, you haven't understood the concepts of CDF and PDF, right? So this is going to be 3 plus 2 kind of a rubric. Dr. D again might have a different kind of approach to this entire problem. So similarly, marginal values, marginal what? Marginal, we are finding out marginal PDF. Okay. So marginal PDF, as you know, is like we are trying to actually see how a specific value of a variable change if only one set of variable is being observed, right? And I know it kind of is a little bit fuzzy logic kind of from here, from this standpoint. But the point now is that we are trying to get rid of one variable, right? So if I have x, I'm trying to get rid of y. And we are going to try to get rid of it by the limits of the equation, that is 0 to 1. Okay. Why? It's almost like integrating out that specific variable that you do not need. Integrating out that specific variable that you do not need. So that's the basic idea behind it. Okay. So again, integration, I'm not too interested in doing that. So if you do this entire integration from 0 to 1, you'll find that first of all, you can again start solving by the same method that we have. First start with x and then go to y, or start with y and then go to x. So we are going to stick with this old method that we have, x squared by 2 plus xy. No, this is, hang on. This is like x squared by 2. Oh, this is y squared by 2. Okay, never mind. Yeah, because we have y equals 0 to 1. So y squared by 2, and this is xy. Yeah, I might be wrong. Just check this one again. But anyway, so anything that you actually take in, this is from basically 0 to 1. Okay, so if it's from 0 to 1, what does that mean? That means that, well, xy is there, right? And x square is there. So this one will be y. Only just the y is variating. We are trying to get rid of the y. So y is going to be half plus 1. Oh, so then that means x. So if you similarly do fy of y, all right, x equals 0 to 1, xy dx. Okay, so this one is x squared by 2 plus x, y, I guess from 0 to 1. So now only the x is variating out here. So half plus y. Yeah. So this is the marginal PDF. Once you actually understand the marginal PDF concept is that there is only one variating parameter. Whatever parameter you write inside the bracket, you integrate out the opposite parameter. Whatever parameters you write inside the bracket, you integrate out the exact opposite parameter, because we are only trying to see the distribution of x out here, because we are trying to study the marginal density of x. Similarly, only the marginal density of y. So that's the point. So this is your part C. Part C, let me see. How many points does it contain? Because I'm trying to basically see if we can make the maximum points. So part C, the marginal PDF and CDF, also contains 5 points. This one is a little bit more complex because I have 2.5 and 2.5 out here. But again, he might have different other sets of scoring rubrics. So I'm not too interested in that. I'm interested in the fact that both of these parts should be correct. Now let's move on to the bigger part of it. The bigger part is basically to, actually I need that, so let's keep it here. The bigger part is to basically find out the probabilities, all right? So what do I mean by that? The next stage is to basically, and this one will have higher points in this allocated, P of x less than y, okay? Or maybe you can try to find out the P of y less than x squared. You can basically do this at home. You know, the solution to this particular problem is already given, provided to you. You can basically practice this. I'm going to just show you this one, okay? Now Dr. D has a bad habit of, or rather a very notorious habit of sometimes actually asking for the plots of it. So do not get scared when you're asked for plots, when there is an inequality or some kind of, not an equal to basically, associated with any of these specific values or any of these specific probabilities. So what happens is that this can be treated as, if you treat this as equal to, right? Y equal to x means it's the straight line, right, passing through the region. So anything that is less than that, you can imagine the area of operation of that, right? Similarly, y less than x square. X square is like, the shape of x square already. So that is less than that specific, whatever curve that is. So the region of interest will be under that zone. All right. Oh my gosh. All right. So let's get going. So one thing that I'm going to actually make you all a little bit aware of is that if you are given to sketch, okay, you have to basically, first of all, draw the graph, right, or plot, all right, and then you have to mark the region of interest. So both, you cannot just draw a plot and keep it there. You have to mark the region of interest. So for this specific problem, y less than x less than y, I'm so sorry, this is like a particular plot, right? So this is a line through the origin. Now if I say x less than y, what does that mean? Every value of x is always less than y. So it's this region of operation, right? Any value, so x is variating, y is variating faster, basically. So all the y's are always greater than x. So this is this portion. Now, many students have in the past come up and tell me, how do you know? Like, you have practiced this probably 1,000 times, but how do you know this, right? Um, in the exam center, it's kind of a little bit difficult for us to actually know this exact thing, but then you can actually plot it. Like if you take a couple of values of x and y, and if you variate this, synchronously less or whatever, you have to maintain a straight line, of course. So if you variate this according to some measures and then plot it, you will actually find out that the region of operation is this one. So for all you folks who are wondering how to determine it, plot a couple of values and you'll see that okay, if X is moving fast, Y has to move triple times faster or double times faster. So this has to be the region of, if X would have been moving faster than Y, this would have been the region of operation. But this is the region of operation that we have. So just putting it out there in case we are asked to sketch. All right. Now, from this region of interest, remember, we also fix the integration limits. Okay. So how do you actually utilize this one to fix the limits of integration? Let's see. And guys, this is going to be a long session. Might actually extend till 8. So let me know when you want to take a break. Otherwise, I'll just continue. Okay. Um, So remember that we are trying to actually now find out the limits of integration. Okay. So your step one to this problem is to find out the correct graph and then the correct region of interest. So this is the region of interest that you have. All right. The region of interest, and then you come to step two. The step two is basically to find out the limits of integration. So we are fixing the limits of integration out here. Okay. Why are we finishing the limits of integration? Because we need to find out probability of something is a value, right? So probability of x less than y, what is it going to actually give you? It is going to give you a value. CDF gives you an equation in x and y. Probability of something is also a CDF, but here you are specifying that any of these y's are always going to be less than x. So that is why we actually can substitute this with the limits of integration correctly, and then we can try to find out the value, because probability is, remember, a value. The cumulative distribution function is an equation in x and y, because x and y are the limits until which we can actually go, and then that's the upper bound, right? So those bounded equations are basically going to be an equation in x and y. All right. So this one will have a value. And again, that is one of the major mistakes that students do make. So make sure that you don't do it. All right. So now, well, in general, right, you know that 0 less than x less than 1, 0 less than y less than 1. Okay. So what is new about this region of interest? We already know that, again, I hope this is getting captured correctly. We already know that this is the limits of integration that is given to us, right? So what is so new and innovative about this specific region of interest, and why do we need this specific region of interest, or more importantly, why do we need this operation or integration limits? Why can't we just put 0 and 1, 0 and 1, like we used to actually do when we were trying to find out the value of k and then move on? No, because this particular probability is different type of probability. We are trying to find out all the values, probabilistic values of situation where x is always less than y. That is why our limits of integration might change. So let us actually talk about the limits of integrations of x. So x has nothing to do with the y. X is just less than y. So x will have just similar integration limits as previously stated, 0 and 1. Why? Because x is not dependent on any other things. In fact, y has to be greater than x always, right? So x might be from 0 to 1, but what about y? Y also starts from 0 because x starts from 0. But what about the upper limits of this one? That's an interesting question, right? Because now we don't know what is the upper bound of this one, right? You know that you sit on this line y equals x, but then how do you interpret this, right? So remember that when you talk about like regions of operation, this is this is bound by 1 as well, right? You cannot go beyond 1, right? This is also bound by 1. Now x can be bound by 0, but then you have this straight line going on. So whatever square that is getting created with 0 1 0 1 out here, That's the region of interest. And within that region of interest, you have a straight line passing through the origin. And then you're told to find out that all the values of y greater than x. So it's this region of operation. All right. These are the four things. So x equals 0 to 1. That's one set of parameters. And I'm so sorry, y equals 0 to 1. That's one set of parameters. What about x? So y equals 0 to 1 because you just start walking. I'm so sorry. Completely delirious and sleep deprived. So you start walking in this line. You continue walking and you reach 1. So y equals 0 to 1. What about x? Because x, you start walking from here, but this region is not included, right? This region rather is included. So if you start from 0, what are the limits of x? X cannot be greater than y, right? So any of the upper limits of this particular x is always y, right? X cannot go beyond y, all right? So now just write the entire equation and solve. So first solve the inner bracket, then go on to the outer bracket. First solve the inner integration, then go on to the outer. All right. So you can do it any way you want. I mean, again, it depends on how you choose to solve the problem. I can, if I were you, I would change the integration a little bit. I'm going to send the y outside basically. So I'm going to send y equals 0 to 1, and I'm going to send x equals 0 to y. I'm going to try and solve for x first, and then substitute that with the values of y, and then solve for the y again. Anyway, I'm going to give you the answer of this one is 0.5. Again, working of this problem is there in your solution manual. Please go through that. This is not going to happen in one day. You need to practice. You need to sit and practice this kind of problems. Again, so y is less than x square. Y is less than x square. The region of operation is just a parabola, right? Now, this time y is less than x, whatever, even if square, cube, doesn't matter. So now the x is variating much more faster. So this is the region of interest, all right? If that makes sense, okay? So similarly, just like this problem, you can also solve for p of y greater than, I'm sorry, p of y less than x squared. All right, so if you solve this, again, this value is 0.35, whatever. I mean, I'm just giving you the values because we are going to require this later or something. Something will happen. I don't know. I have to see the problems. So let's actually open the book. All right, we are trying to solve 5. Let's see. Okay, we are trying to solve in, let me just go to that region, join CDF and PDF. Yes, I have found out. Yes, okay. No, these are two signals. Yes, okay. There's also another thing, x plus y less than 0.5. It's the same thing. You just take, either you take y less than 0.5 minus x, or x less than 0.5 minus y, and then proceed with the problem. So everything is about the limits of integration of these things, okay? Once you set that, the values will automatically come out, because this integration, you can do it in your calculators as well. So integration is not a problem, big problem. The problem is the limits of integration, because if you put 0 to y squared or 0 to 3, the limits of integration is going to determine the values of the integration, right? So that in that way, this is much more critical. So the part E for this problem, I have to basically see the homework because I have given something else. Right. So the part E of this problem is that find the correlation and covariance of X and Y. So the correlation and covariance, you see, I haven't basically given that part to you. So what we are going to do is we are going to actually take up a certain steps, okay? Find the correlation. Sorry, what did I give you? Find the correlation, covariance, and indicate whether this is independent, orthogonal, or uncorrelated. All right. So first of all, you have to find out the covariance. First of all, you have to know what are these covariances, correlations, and everything else. In fact, this is a very important concept for your project 2. In your project 2, you're going to deal with values of images. So you take an image and you record that in your MATLAB, and it's going to be a matrix. It's going to be a matrix which has one set of X values and one set of Y values. Okay. So correlation, as the English word suggests, is how correlated is one data to another. That means if this is varying, on what basis is this varying? Or if this is changing, what are the characteristics or correlation between this specific value and this specific value, right? So covariance and correlation, these have very specific formulas, and we are going to basically first look at the formulas and try to actually solve them out there. Again, formulas are available very readily at the back of your exam, right? You don't have to bring your cheat sheets or any other things to the exam hall. You just basically, yeah, if you want to actually bring an integration or differentiation, a paper or two of that, please talk to Dr. D, because I would have definitely tried and given that problem, solved that problem by giving you the sheet, but then, I'm not taking the exam. All right. So first of all, find out the correlation. Formulas will be again given at the back, right? So first of all, even before you talk about correlation, you have to basically find out. So let's actually write the covariance formula. You will actually know what I'm talking about. So basically, it can be written in various ways. So if you take Dr. Mandry's class, he is basically going to define it this way. Y minus EY. And by Dr. Mandry's class, I mean neural networks or any other sorts of subjects like that. If you take his subject, he's going to basically define it like this. Okay. Now you can rewrite this in many formats, but a very famous format to use is EXY minus EX EY. Okay. Even before you go here, all right, you are going to have some basic problems, probably at the beginning or at the end of, I am trying to see where. So you are going to actually basically learn how to deal with the expected value operator in your homework 4. Okay. Now, why do I say that this is an operator? Is because of this. So let me actually see if I can pull up the homework 4 again, because of a certain reason. Let's see. So if I actually give you, by the way, Markov and Chebyshev inequalities, you can basically ignore them unless professor has very specifically conducted those lectures in the class. I know that I have given you some problems on Markov and Chebyshev inequalities. You may choose to actually not revise them. All right, let's see if I have a good problem on expected value. I think it's either there in homework 4 or 5. I might be wrong. Let's see. Yeah, I might be wrong actually. Let's find out. Yes, I'm absolutely wrong. This is actually there in your homework 4. So if I actually recall 4.56, okay, if I have y equals 3x plus 2, okay, so this is also a function of one random variable. And I'm explaining you through one random variable because the two random variable is exactly work the same way. Okay. So first of all, if you have to find out the expected value of y, so expected value is basically an operator. Now, what is the definition of expected value? You are taking a sample mean, right? And then you are trying to find out you're taking a sample and then you're trying to find out the mean. Now, is it equal to the average, right? So if you have, for example, in a class you have 50 students, right? And in that class, I'm trying to basically find out the average age of students, right? Or the average height of students. You know exactly that there are 50 samples. You know exactly that how average is done exactly. But say, for example, you have a sample mean. Now you have 40 students present. You know that there are 50, but you're anticipating 40 students and you're trying to basically see what is the expected height of this particular class. It's some concept like that. Okay. So the expected value of y, if you take this expected value and I'm applying the expected value operator right across the board. So it's almost like whatever you do on the LHS, you do the same thing on the RHS, right? Hang on, guys. Just one teeny tiny second. I'll be mute. All right. So now the expected value has no um, interest or no effect on constants. Okay. So the constant can be basically shifted out. First of all, you can basically divide the expected value like this. Where's the problem, dude? Yeah. So find out the expected value. Yeah. Okay. So the expected value, first of all, can be shifted. Now, yes, you can say expected value of 2, but expected value of 2 is 2. So 3 times expected value of x plus 2. That's how it exactly looks like. So the expected value basically sifts through the entire sifts through this entire bracket, whatever is there inside the brackets, and it only operates on the random variable. So this is a random variable, right? Only operates on the random variable. The rest is basically sifted out. All right. That's how the variance and the expected value operator basically works. So if you have to find out the variance of this one, the same thing. Okay. The variance exactly works the same way. So now, if I find out the variance, for example, all right, say for example, I have to find out the variance of 3x plus 2. Same thing. This is only going to sit at 3 variance of x. Because variance of 2 is like, not there. So what is going to happen is that you have to be a little bit more careful. Actually, I made a mistake here. So this is variance of x. So if you have to throw out the constant outside the bracket, it will become 9. Well, why? Because variance is always dealing with x squared. We'll see about this. So the point now is My point is not to show you how to actually calculate the variance. My point is to explain you that the expected value and the variance is basically operators that can be shifted across through the brackets of whatever you have inside. Now we are actually going to concentrate on the covariance because that's what we are trying to find out here. But why did I actually talk about the expected value is that you can actually see that we have to calculate the expected value of x and y out here, right? As well as xy. So how do you calculate all these things? That's interesting, right? So again, these problems, if you're not comfortable or you haven't worked them out properly or whatever, that's okay. But this is how you do it. And this part I'll upload it tonight as an additional portion to the original solutions. I didn't quite realize that I did not upload that. So now you have the covariance, right? So basically what you do is, well, the expected value, first of all, let's start with the expected value, right? The expected value of xy is basically general. This is general definition, okay? So general definition is minus infinity to infinity, minus infinity to infinity, x, y, f x, y, x, y, dx, dy. Okay. This is the general formula again. Okay. And why are we trying to actually find this out? Because covariance of x, y is basically the expected value of xy minus the expected value of x times the expected value of y. How do you find these out? Expected value of x is marginally minus infinity to infinity x fx of x dx. So x is basically whatever x you have in your equation. Fx of x, this is the marginal density. Now, where did you actually get this marginal density? Remember that, whoops. Now remember, when we were actually trying to work this entire problem out, we actually came across, let me see. Yeah, we actually came across the marginal densities, right? So the marginal densities, if I have to really put it, so this one will be, when you're calculating the marginal densities, be careful of the limits of integration, okay? So expected value of x is of region of operation is 0 to 1, x plus half dx, and region of operation of y is 0 to 1, y plus half dy. Okay. Again, I'm not going to solve these two out. You can basically, this is plain integration, right? So once you actually come across that part, or once you get across this hurdle, similarly, let's try to get across the hurdle of xy, 0 to 1, 0 to 1, xy, well, this is fx of xy, so I have to basically see what that means. Oops, where is it? Oh, there you are. What did we start with? Now I completely forgot. Oh yeah. So this is k of xy, right? So xy times x, oops, xy times x plus y dx dy. Okay. So as you can see that this is a value, this is a value, this is a value. All right. This is a value, this is a value, and this is a value. All right. So covariance, when you calculate that, it will also be a value. All right. This part should be clear. Now, that's the covariance calculation in general. Again, the variance calculations, we are going to get to the variance part one step at a time. But we have like, in the meantime, just in the meantime, since we are talking about e to the power of x, if, this is not there in the solution, I'm going to upload this tonight. If e to the power of, if exy, if this calculation is by any chance a 0, okay? If by any chance this is a 0, then they are orthogonal, right? This part should be clear. Now, in case, now let's go back to your marginal densities, right? So the marginal density, if you have a joint PDF, right? Right? From here, you have split it into fx of x and fy of y. Just in case, if you multiply fx of x times fy of y and get back fxy of xy, that means you're multiplying these two functions to get back your original PDF, then they then the what was the question, dude? Okay, now to go back and see the question. Homework 5. Yeah. Then the random variables are independent. All right. So this one is orthogonal. This one is independent. Okay. Now, you can state this at the end of the exam as well, or you can state this as you solve it, however you please to. Okay. Now, for the variance again, variance is just x square. All right. So instead of x, you have x square. Instead of x is, I'm so sorry. Instead of y, you have y square. Instead of x, you have x square. That's all you have for the variance. So same formula, same limits of integration. Instead of x, you put x square, and whatever else other function stays the same. So that's with your variance. Now, what are we trying to actually do with this entire thing is to calculate the rho of xy. We are calculating the correlation. Actually, when I usually take a lecture, this is where my lecture actually starts, because there is a huge study of the correlation coefficient. And what happens, because this is bound between two values, right? And what happens when this is -1? What happens when this is 1? What is it? What is the essence, or what is the significance of covariance? What is the significance of correlation? And why are we learning these, right? So these are much more in my lecture notes. But then that's fine. I can just share my lecture notes, and then you can read it at your own time. This is not probably very important for your exam. But anyway, so sigma of xy, rho of xy, I'm so sorry, is basically covariance of xy divided by sigma x and sigma y. This is the variance, variance of x, and this is basically the variance of y. Right? So if you go over the last lecture that Dr. D actually presented, he went over several problems. In fact, let's see. So if you really want to practice, and this exam requires a lot of practice, so it won't be a terrible idea for you to go over all the lecture material and practice everything, okay? Yes, so in this case, he actually covered quite a lot of problems. I'll give you the problem numbers that you can basically practice from your book, or you can practice these problems that I'm covering out here today, right? Same thing. So you can practice 5.31, 5.46, 5.48, 5.65, and 5.66. All right. This exam is going to require your practice. You cannot win this exam. Okay. So these are your practice problems. This will definitely contain some parts of expected value, variance, covariance calculation, and correlation coefficient. Right? And then basically the correlation coefficient will give you the magnitude, and there's a concept of magnitude and vectors, basically magnitude with direction and magnitude only. So those kind of concepts are going to be expanded in my slides if I upload them, if I find them, and I'll upload them. If you are interested in why are we learning correlation and covariance, you can basically follow the slides there. Not now, I'll suggest you after the exam. So for the exam, again, this is going to be a 40 points or 40 or more points problem. First of all, find X or find K, right? And then from there, find CDF. And from there, find the marginal, right? Marginal PDFs, right? And from the marginal PDFs, you can, you can, I mean, go in various directions. One of the directions that you actually want to go towards is basically you have to find a probability, right? X less than y, or p of y less than x squared, or whatever. It can be anything. And from there, this might be a 5 point, this 5 point, 5 point, this might be a 10 point problem depending on how many you're trying to solve. And then from there, you have to basically find out the covariance and correlation coefficient. That might be a 5 point plus 5 plus 5, 10 point problem as well. And then you are trying to find out whether this is independent, orthogonal, and all those other stuff. Okay. And this solutions, the solution for this one, solution for this will be uploaded tonight. So check your canvas tonight. I'll upload this. All right, so this is one of the major problems that you solve. So we have solved two problems till now. One problem dealing with problems regarding finding the PDF, I mean, first of all, the CDF, and then the marginal PDFs of two random variables. And then we have also done functions of one random variable. That alone should be covering at least 60 points. Even if you just do these two problems, it should at least cover 55 to 60 points of your entire exam. All right. So, take a note of that, right? Now, the other parts to this entire problem is, I mean, you can actually also find functions of two random variables. This is not function of two random variable. This is just a simple PDF CDF problem that you actually got in exam 1. But this particular problem might be followed by a function of two random variable. So that might be a little bit complicated again. And we are going to actually work a very famous problem. And this problem has also been worked out in your Tuesday's lecture by Dr. D. Whichever method you try to solve or whichever method you try to follow, it's the same thing. In case you want to follow his method of approach of solving the problem, it's the same approach. Basically, the understanding, I explain a little bit more because I know that some of us, we struggle with the region of interest a lot. And this is from my past experience from the different students that I have interacted with. Even the best of the best students, they actually struggle with region of interest. So that's why I kind of go over these problems really slow. It's not that I'm doing a different solution than Dr. D. It's just that I'm explaining a bit more so that we are a little bit more careful. That's all. All right. So, well, let me see how to approach this problem. We don't have like a very generic thing. This is the marginal PDF. So marginal PDFs can be found out anyway. So that's not the main concern. So let me actually see how to solve this one. Or do we have a function? Let me actually open the book and see if we have a good example of functions of two random variables? I'm pretty sure we do, but then independence. Let's see. I don't know why I didn't give that problem as a part of your problem set. Let's see. All right. Let's not solve 530 then. Let's actually directly go to 599. Okay. This is basically function of two random variables. Now one might ask me that, well, what is the difference between when we are actually working with fx of x or fy of y or fxy of xy, right? What is the difference? Why aren't they called the functions? Well, they are also functions, right? But here the approach is that we have a third variable. Okay, so the first PDF is kind of defined. So this is the joint PDF of x and y. The joint PDF of x and y varies in such a format that it's an exponent. Okay? The region of interest being that 0 less than y less than x less than 1. So the upper bounds of y is x, the upper bounds of x is basically 1, and the upper bounds of both of them is 0. So that's the region of interest that you have. Now it's easy for me to say, but then we are going to draw out and we are going to chalk out the entire thing and see. This problem is a little bit complicated in terms of the region of interest. And remember, the region of interest will basically give you the limits of integration, right? So this is important to understand where exactly is the plot kind of operating in, right? Or where in the plot are we kind of interested in kind of focusing. All right. So why is this a function of two random variable is because we have another uh, random variable which depends on x plus y. So we don't know x or y, but we know the joint PDF of that, right? And we are trying to find out, well, if we do have the joint PDF, can we find out the variable z, which is x plus y? Given the circumstance that 0 less than y less than x less than 1. So this is the problem. Can we even approach this, right? So the answer is obviously yes. You can approach this and we are going to approach it. Now, before I go into this entire problem, please understand that whenever you have a random variable and another random variable that is dependent on another random variable, so this random variable z is dependent on x plus y or x and y both, right? So both are independent or they are variating in some format, and this one is a dependent variable. So whenever you have these kind of things, this is called function of two random variables. So if suppose it would have been z equals x or 3x, suppose, function of one random variable. That's how it goes. That's why it's called function. No other reason. Everything is a function out here. But the point is, how do you start the problem? Great. We have the problem. We understand this is a function of two random variables. We know the region of interest, but how do you start the problem? The first step for your problem is the region of interest. So this one will be step 1. So first plot and find the ROI. Okay. Now, when I say plot, I don't mean that you have to pull out your MATLAB or something like that. It's a rough sketch of what, first of all. Now, there are two parts to this entire plot, so I'm going to actually draw it step by step. Okay. So obviously there's a x and there's a y, right? This part is clear. Now, the first region of operation is we are going to work with the limits. Remember, the limits actually kind of tell us about the region of interest. So 0 less than y less than x, right? So it starts from 0, nevertheless. X also starts from 0, y also starts from 0. Now, y happens to be less than x. That's all it is, right? So if, okay, if y would have been equal to x, say for example, y is approaching x, and then it misses out x by just 1 point, right? So y has to be always less than. What if y is equal to x? So y equals x, basically. Say for example, we take y equals x. What kind of plot is that? That's a plot of a straight line through the origin. So let's plot that. This is y equals x. So y less than x is going to be this region of operation again. I'm not drawing it, but I'm just going to, blankly point it out, right? So anything beyond this one, remember, this is the first problem that we did. We told you that if y is variating in a less space, this is the region of operation. If x is variating in the less space, this is the region of operation, right? We have done this before. Now, for us to actually take this into consideration, we have the first mystery solved, right? What does the second equation look like? For the second equation, you need to know what is the random variable trying to look like, right? So the random variable, what are we trying to find out the region of? The region of interest is basically, if given that the joint PDF is e raised to minus x plus y, then given that, what are we going to do about z, which is x plus y? So, well, the only thing that we can do from here is to find out the CDF. Now remember, CDF is easier to find. It's kind of like the area under the curve until a zone or until a certain point, right? So CDF is much more easier to tackle. And CDF by definition, whatever variable you are trying to find the CDF of, that's how it's defined. So if you're trying to find out the CDF of fz of z, then we define it by p of z less than small z, or in other words, PDF of x plus y less than small z. All right. Here as well, now this is the complicated part. Okay. Here as well, you are going to actually have to understand that this z is just a value, right? This can be 6, 5, 4, 3, 2, 1, but it's z because, well, we are trying to actually generalize the formula because we don't know the random variables. So this is basically as good as an equation if I write x plus y is equal to some constant c. Okay. This is the small z that kind of marks the point on either the x-axis or the y-axis. So it's basically a number, but then we are generalizing it and calling it z. So this is in terms of x and y. All right. So either we change the variable to x or we change the variable to y. What does that mean? And why are we going to be involved in that, or why are we going to be even interested in that? So one line of interest we have got is y equals x from the limits of integration, right? That is not the limits of integration, I'm so sorry, the bounds of the function that we have, right? So the next stage is to what if this PDF or the CDF that we are trying to do out here, that has a bound or not, right? To find that out, you can take it in terms of x as well. So I'm taking it in terms of y is equals minus of x plus z. Okay, we are just trying to actually subtract minus z on both sides. Okay, so LHS RHS minus z. I'm sorry, minus x minus x. So just subtract it from both sides. So that's what we get. Now, why did we change the variables like so? Well, we are going to actually put this entire thing in an equation. I mean, in the integration format, right? So what does that look like? I'll do it and then I'll explain you as I do it. So you see, this is a double integration. So there's going to be two integration signs. All right, that's great. We have e raised to x plus y. Okay, why are we trying to actually get to? I'm going to explain you in a while. We do have dx and we have dy. So that's great. And remember from the earlier examples, when we do have to find out the CDF, we basically have to find out the upper value limits not in terms of basically values, in terms of x or y, or in this case, in terms of some formats of x and y, right? Because this is another random variable. So the complexity of this random variable or functions of two random variable does not really come from the fact that you don't know how to solve the problem. It comes from the very basic concept. It's going to hit your very basic concepts of what is a PDF and what is a CDF. So this is what we are defining the PDF of Z, right? And we are finding terms like X and Y, but then what about Z? We'll get there. We'll get there. Don't worry. We'll get there. Okay. So now we are interested in limits of integration. So why did we write this equation? Well, if you actually go back to your, you know, let me see. I don't know what page it is because I hardly rarely follow your book, but there should be a formula for your PDF, the definition, the very definition of PDF, be it function of one random variable, two random variable, whatever it is, right? It doesn't matter. So the very definition of this particular part is that the PDF, you integrate the PDF from minus infinity to infinity, and then you get the CDF. We are still in the CDF zone, right? CDF integration, right? So this one is formula 511, just in case you want to see. 511 from your book. So the reason I'm actually doing this in this much amount of details is that so that you don't miss out on any opportunities to score, right? And problems are going to keep varying within these zones of operation. I'm going to do another problems on entropy just in case it comes in. But this is the set of problems that you are going to get because I've kind of went through the entire, uh, Tuesdays and Thursdays lecture. I think he's basically trying to provide you with exam problems that are going to be in this vicinity. All right. So that's why it's important. Right. Excuse me. All right. Back to your problem. Limits of integration is important. So the first limit of integration that we actually put out here is either select X or select Y. All right. Now, the other bound of this particular equation, we haven't said it. This bound actually states only this particular part. That is the PDF zoned out with only X and Y values. But we are not interested with just X and Y. We are also having another parameter Z, which is dependent on X and Y such that Z equals X plus Y. So, well, if Z equals X plus Y, and we have kind of made this kind of substitutions, right? That Y equals minus of Z plus, minus of X plus Z, what does that line look like? What if we actually have, we imagine Y equals X minus of X plus Z, all right? What if we imagine this line, all right? Now, I know that people might actually, some of the people actually struggle with the plots of these things. So first of all, imagine minus X, okay? So it's like -1 and then it runs out here. And then you kind of go Z times up. So you are going to basically find a line like this, all right? Now, the cross point of this line and this line is at an intersection. So intersection, if you solve this simultaneously, these two equations, you would see that the intersection point for this one is basically Z by 2. Okay. Why is that important? We'll know about it. Don't worry about it. And then if you actually, so this line is basically Y equals minus of X plus Z. Now, why am I interested with this line? Well, the equation, the final things that we are trying to do is in terms of Z, not in terms of X and Y. This is function of two random variables. So the z parameter needs to be introduced into the curve or introduced into the plot so that we get the upper bounds or the other bounds of this function. The first bound is that the function, the PDF itself, is bounded by 0 less than y less than x less than 1. So that bound, we have to respect that bound. Now z itself, do we have any variating parameters of z? Well, in terms of y, you can take it in terms of x as well, no problem. So in terms of y, when you actually take that equation, you would see that you are basically y equals minus of x plus z. Although x, y, and z, all of the three are random variables, you are basically variating the parameters in such a way that you take it in terms of either y or in terms of x. Okay, although z is unknown. Now, if you solve them simultaneously, you got a midpoint for this line or the point of intersection for this line. All right. So we can safely say that the function is available on this side of the line, but it's bound by this side, right? So the zone of operation for this function is this. Trust me, this is going to be very difficult for you to find out during the exam if you do not practice these kinds of problems. Now, in terms of practicing these kind of problems, your book doesn't do a really good job in assigning a lot of problems like this. So I'm trying to, give you a good set of problems to basically practice. And I am failing to do that. So, I mean, you can actually do a little bit of problems before you actually take up this problem, because this problem is a little bit complicated. Let me actually tell you that very right away. But you can do some of these problems. Now that I see that 5.95 could be an attempt, 5.94 could be an attempt. So we'll see. If I have time and if I have the energy, I'll definitely actually cover one or two problems so that you get used to the idea of the functions of two random variables. All right. So now, so the second bound is, the first bound is this line, the second bound is this line, and the region of interest kind of lies in between that. Okay. Now, okay, great. Now what? So now we have to actually basically see that this is a triangle, right? It's some kind of a triangular zone, right? So basically now, whatever we do for this triangular half, we can actually replicate this for this triangular half as well. Yep. So in that terms, in that parameter terms, we are going to actually try to define the one triangle that we have and then multiplied by 2 for two of the triangles. So this triangle is what I'm interested in. I'll also multiply this triangle along, all right, to get the region of interest. So we are only operating within this triangle zone, okay? We are not going outside that. Now, for the regions, for the interest, what is this value though? So if you put x equals 0, this will be z, right? Just for the interest. So this 2 parameter comes from replicate this for the other triangle. All right. So we have two triangles. We are trying to solve for one triangle and replicate this for the other half. That's why it's 2 multiplied by. Okay. Great. What are the bounds of operation? So let's look at this triangle, just this triangle. So this is 0, z by 2, and well, this is bound by z by 2 as well, right? So what do you think should be the values of x? Remember, this is the region of operation, okay? Not the entire zone, okay? So the value of y is actually easy. The value of y is 0 to z by 2, right? But the value of x, you cannot say it's 0 to z by 2. That means it's going to include this triangle as well, and it doesn't include that triangle, right? So let us actually try to combine the very fact that we have this triangle, right? So what is this line? This line is y equals x. Where did this come from? This came from the limits of 0 less than y less than x less than 1. Okay. Now, and this, there's the other line sitting right out here. I'm not going to draw that line, right? Um, well, I mean, mm, to understand this, so the x can crawl up to here, right? Well, then, but it has to miss out this part. So this part is not included in it. So it's almost like x needs to start from y because x cannot be less than y, right? So let's put down y. But what is the upper bound of x, right? It cannot be certainly 1 because you can put as 1, but then you cannot put the, because this is z. This entire equation is the CDF of z. So the CDF of the lower bounds of the x can work, that okay, x has a lower bound, but the upper bounds does not work because this particular line is there. So maybe the 1 region is much more greater than z, right? Or maybe less than z, doesn't matter. So this is the upper bound of x, not 1. So people actually got a little bit confused when I was explaining this problem a couple of times. So 1 was the older limit for the PDF of xy. Now we have to find out the newer bound. Newer bound is limited by x minus of x plus z. That is y equals minus of x plus z is the new limits for the lines. So x cannot be more than z minus y. So where does this z minus y come from? So if you solve this equation, you will see that y minus of z is minus x. So x equals y, z minus y. So almost like from this bound, instead of putting 1 as the bounds out there, we are putting this as the bound, z minus y. So the limits of integration, again to write it clearly, this is 2 times because both the triangles are required. Integration of y can traverse from 0 to z by 2. So that's z by 2. And x, what about x? It starts from y. It goes from y to z. Y to z, y. X is greater than y, but not greater than z minus y. Where does this z minus y come from? Y equals minus z, minus of x plus z is the upper bound. Where did this upper bound come from? Well, this actually came from the entire equation that z is equals to x plus y. This was the entire premise of the function of 2 random variables, right? So if you actually take those 2 random variables, then you have to basically make substitutions and get to the PDF. I'm sorry, CDF of this, and then CDF, from the CDF we get, okay, well, uh, then we found out the CDF, and from the CDF we get y is less than, so let's substitute that with equal to minus of x plus z, and then x is equals to z minus y. So that's the highest limit for x, because x will traverse from here and will hit this line. Y is going to start traversing, already it's bound to 0. So y is almost climbing this ladder here. Like y has been displaced from this zone to this zone. So y is almost climbing from 0 to z by 2. X is basically going in this direction. So almost from anything that has to do with less than y value, and it's kind of hitting this line. So x is traversing and going here, y is traversing and going here. That's the region of interest. That's why the integrations are so different. And then we have e raised to x plus y, and then we have dx dy. So until and unless you understand this one, repeat. This is your step one. That's why this exam is so difficult, because these problems don't take much time for me to actually work out once you know the region of interest, but to get to that point, you need practice. Okay. So once you actually achieve the exact CDF, you can go ahead and integrate this and actually find out the CDF, right? And CDF again is going to be in terms of, so first of all, you have to solve this. So if you remember the law of indices, oops, um, well, I mean, I wouldn't teach you how to exactly solve this problem, but then I'll show you how to actually tackle this, okay? So this is outside the scope of my syllabus, but anyway. So this one is y, right? So let's actually separate the y's out. So by the law of indices, you know that e raised to x plus y, you can write it as e raised to minus x, and so on, right? This is the law of indices, one of the properties of law of indices, right? So by that principle, separate out the y, and then you have to separate out the x, right? So if you separate out the x from the y, what are you remaining? Y z minus y, right? Now you solve this one or you solve this one, and 2 basically multiplies both. Now you solve either of them and then start tackling the inside bracket. So what would this look like though? 0 to z by 2, e raised to minus y dy. So this is e raised to minus x minus y z minus y, right? So 2 0 z by 2 e raised to minus y dy. Let's send the dy outside. This one will be e raised to minus y minus e raised to y minus z, and then you go on solving that, right? Then you multiply it and solve for dy and etc., right? So you should arrive at some kind of equation which actually, like, you solve all the steps, right? There are multiple steps in here, and then you arrive at 1 minus e raised to minus z minus z e raised to minus z. Okay. Now this is an important step because you now found out the PDF, I'm so sorry, CDF of the random variable, right? So from here, you have to find out the PDF. Remember the question, if it stops at CDF, you stop at CDF. There is no point in calculating the PDF. But PDF can be done in one step, right? Because you have to just differentiate the CDF, which is basically e raised to minus z minus e raised to minus z. Oh, plus or minus, wait, hang on. E raised to minus z e raised to minus z is a minus, plus, again I'm applying chain rule for this one. This one is 0, right? This one is e raised to minus z with a minus sign, so that's plus. And then we have minus e raised to minus z, which is this one, and then plus z e raised to minus z. Whatever, I mean, you can solve this one for z greater than 0. Okay? This is your answer. So this is not a tough problem as such, because once you get to the point where you are comfortable with solving the integration problems or the region of interest especially, you are good. But to get to that stage, you need practice. Okay. Let's see. Haven't I given you 110 solution? Oh, I see. Okay. But I do have to upload the solutions as well. So in homework 5, there's another problem where you are given a specific Gaussian random variable, and same thing, you have to find out the variance of x, you have to find out the variance of y, you have to find out the variance of covariance, in fact, of x and y. It's the same problem. Whatever the PDF given to you, you have to follow the same process. You have to first of all find out the CDF, then find out the marginals. Yes, find out the CDF, or you can basically directly find out the marginal PDF of that, marginal PDF of X, marginal PDF of Y. So that solution, surprisingly, I have not given in. So I am actually updating the solutions tonight immediately as I go back, right? So other than this, the practice wise, like if you really want to practice these kinds of problems, it's good for you to start with practice. Um, I would say 5.95 and let's see if you have a good problem. Yeah, I mean 5.96 is also not a bad problem. So please practice these problems, okay? So when I say practice, what I'm trying to say with practicing these problems is that this exam you need a lot of practice. So by looking at this specific video, when you actually get to look at it, you need to basically sit and absolutely clarify the concepts of expected value, variance, covariance, correlation coefficient, and then trying to actually amalgamate that and finding the values of this. And then we are actually going to end with entropy. We are well within time. I promised you 7:30, but then I started a little bit late, right? So that's fine. We can hang around a little bit more, right? So the entropy problems, unfortunately, in your book. So if you ever take up statistical signal processing or digital communication or any sort of communication courses under Dr. Liang, Dr. Skizes, Dr. Mandry, so you will be actually requiring the concepts of entropy. And entropy is a very easy problem to tackle. So we are going to actually work on that one. Example wise, in your book, let me see if I can search for a problem for that. There are actually good examples on entropy. So you need not search like hither hather with what type of problems to practice for entropy. But there's a very famous problem that we actually kind of do for a very intricate, like this is the very basics of digital communication again. So for that, let's actually end our session here. So entropy, for example, why is it important for us to calculate entropy? Basically, if you are interested with networks and bits and how many packets are dropped and all those other networking theory, or you're interested with how much of information content is there in a specific message signal if you're transmitting from a specific location to a receiving location and all those other things, then you are also going to be actually interested with entropy. So first of all, the formula for entropy is very, very simple. What does it say? Basically is this, that it looks complicated, but it kind of says that if h of x is given by the entropy, it basically is the expected value of the information content. Now that doesn't make any sense. So entropy is basically, again, calculated on a very digital domain, okay? So here is where your discrete random variables are going to be in use, all right? So entropy is calculated by a summation. Why? Because usually the bits are represented in zeros and ones, and one bit is transmitted one after the other. Even if it is like a hex code of, the word no or the word yes, it's like a hex code. And then from the hex code, you actually transfer that into a binary like 110111, etc. So those are basically summations, and those summations are basically over a range of values, and those range of values are called something. It's not important for your probability course, but it basically is x equals k. Remember that when you are operating in the domain of discrete random variable, you can actually use the word equal to log of probability of x equals k. Now that doesn't make any sense, but let's say, for example, you have a problem in front of you that there's a binary representation of a random variable. Okay. So example is, you can actually take up the example of 460 in your book, and that's exactly what I'm doing. So if you have like x as like, 0, 0, 0, 0, 0, 1, 0, etc., you get the point, and all the way till 1, 1, 1. So these are 8 numbers, 0 to 7, right? So this is 0 to 7. And I've taken 3 digits to actually represent them. Okay. So if I give you to calculate that what is the entropy of x? So what is the entropy of x? All right, question mark. So how do you calculate it? Well, first of all, you need certain things. First of all, you need the probability of x equals k. What does that mean? Well, k out here means the amount of values that are there. So there are 8 values, so 0 to 7, right? So you need all the probabilities of all of them. Now, in the problem, usually there will be stated that all the values of x is equiprobable. Remember, we actually came across this term when we were actually solving problems in our first term. What does equiprobable mean? Equiprobable actually means that if you roll a die, all the 6 surfaces of the die is equally probable to appear, which means the dice is not biased in any format. That's all it is. So any of these digits that are there, they have the probabilities, similar probabilities of basically getting transmitted. All right. So now from there, picking up from there, so what does h of x do? H of x is a bunch of probabilities, right? It's negative, first of all, right? Um, probability, log of the probability, right? Now, people often confuse the word ln out here. Yes, it is defined by ln, but basically what we are trying to say is that log of the base of whatever digits we are transmitting. Say, for example, we are using zeros and ones out here. So we are going to use log 2. If we use 3 digits representation, 0, 1, 2, for example, we would use log 3. So similarly, what about the probability? What about this probability? Well, it's equiprobable. There are 8 options. So each of these options are 1 by 8, right? Why is that so? Why is that so? Well, if a coin toss results in half head, half tail, 8 equal probable things would result in 1 by 8 each, so that the entire probability adds up to 1. That's what your entire aim is. So then, log 2 of 8, and you have to just keep repeating that, right? 1 by 8, log 2 of 1 by 8, until you reach all the other 8 values. So this is 1, this is for 0, this is for 1, and then you'll have 1 by 8, log 2 of 1 by 8. This is for 7. And then you find out the value of this one. Say, for example, the value of this one is 3. What is the unit of entropy? Bits. So what does this mean though? Right? What does this imply? Well, I mean, you don't have to actually know what it implies though. But the entropy of a random signal, you know that it's defined like this. And so think of it this way, that when a message is getting transmitted, there is a possibility of uncertainty that the outcome is going to not exactly be as we have transmitted, right? So we are trying to actually calculate the information content of it, hence. And why is it the expected value? Well, there's another whole discussion on that, but I'm not going to get into that because it's exam. For exam, you have to remember that just the formula is there. The formula will be given at the back of your exam if the entropy problem at all comes in. And you have to basically just gather the probabilities and then take log 2. Why log 2? Well, because whatever representations are there, sometimes it will be log 3, log whatever. So as many representations are there for each of these probable options for the random variable, that is the base of the log out here. Okay. Now, The problems that are there in your homework, however, 4.147 and 150, they are a little bit different. Those probabilities are, you can practice them as well, just in case you want a different flavor of what types of problems exist in the entropy calculation. You can do that as well. But basically, what entropy means is the information content of it. That is why it's represented as I of x, information content of the random variable that is getting transmitted or whatever. So the 150, it kind of deals with the coin toss experiment with a biased coin or with a biased possibility. And I think the 147 problem deals with the outcome of, again, a fair die. So each of the outcome is equal probable. And if you are trying to find out the conditional probability, then it might be a little bit different based on the conditions. So again, entropy will be a very one-liner, very simple problem, very straightforward. Okay. Other than that, I don't think we have to get ourselves concerned with any other topics. So we have functions of one random variable, the general concepts of CDF and PDF for two random variables. And under that general concepts, please study the marginal PDF of X and Y, expected value of X and Y, expected value of XY, like both the variables together. And then with the help of that, try to actually calculate the covariance. After you calculate the covariance, try to calculate the variance. Variance and covariance is different. Please see the formula in your book. And from there, also try to calculate the, actually, let's see actually, if you do one, let me see. Actually, if you attempt to actually solve these any one of these problems, you will be encountering the variance covariance concepts at least once, at least for 5.65 or 5.66. I can basically verify that for you as well. Let's see. Hmm. Let's see. Again, don't be too overtly concerned about this exam. Just sit and practice. That's all you need in this exam. Once you sit and practice a couple of bunch of problems and get the gist of it, you are going to be very comfortable. Okay. Oh yeah. I actually forgot one more concept. Now I don't remember where I was doing this. Oh yes, I can actually cover it out here. All right. So remember how we said that if E of xy is 0, this means that this is orthogonal. You already know independent that if f of xy is got back by multiplying the marginal densities, then this one is independent. I actually forgot to mention the uncorrelated one. So the uncorrelated, when you actually calculate the entire value of covariance, which is E of xy minus E of x times E of y, and this basically comes out to 0, then we can say x and y are uncorrelated. All right. Okay. So I would rather say 560 as well. So 560, 566, these problems are going to be of the same type. I would say 560, any problem from 560 onwards, all the way down to 566. If you do that in your problems, like when you're practicing the problem, 560, okay, you know what, I'll give you the individual numbers now that I think about it. Let's see. Because that might be a little bit confusing for you to navigate. All right. So anything from 560, 561, yeah, 561 is definitely going to help you. Let's see. I would avoid 562 and 563. Let's see. I would definitely do 565 and 566. And these are the problems that professor had actually practiced in class, 548, 546, 531. So if you want to practice that, go ahead and do it. But from my sake, these problems are going to be basically the big problem where you start with the PDF, right? And then you go over and you calculate the CDF and then that uncorrelated and that big problem. Okay. Now, speaking about independence, all right, there's an interesting problem that we can actually work out, which actually proves that independence, because sometimes in the exam center, we actually rush ahead too much and we fail to actually observe the independence as well, right? Mm, let's see. I think there's a very good problem in your book. Let's see. Or maybe in the homeworks as well. I hope I have given that in your homework. Homework 5. Yeah, actually the homework 5, the first problem 520, if you work that problem out, that will actually give you a very good idea of what independence looks like. So here we start with a CDF, okay? We have a CDF which is 1 minus 1 over x square and 1 minus 1 over y square for all x greater than 1, y greater than 1, and then we have 0 elsewhere. All right. In this case, we are told to find the marginal x and marginal CDF, of course, of x and y. Okay. Well, out here, you don't have much options in the sense that this is the CDF itself. You don't have very many options of, variating, trying to actually integrate and differentiate and etc. etc. So how do you actually go about solving this problem is, I'm going to try and give you again the book reference. I am not very good with the page numbers and everything else, so let me just navigate that. Let's see. Functions. Oh, this is expected value. Okay, not this one. Let's see. I would select this one. Let's try to see the properties. I'm trying to get to the properties of them so that I can give you the exact property. Unfortunately, that is not happening that easy, is it? Well, if I cannot give you, I'll actually show you what to do in it. But then, well, I don't get where is it exactly stored. So I'm going to just give you the exact problem solution for this one. And the solution is obviously always available in your, in your solution manual as well. So, well, if you have to basically select the region of operation for this one, although not asked specifically, you have to basically first of all plot, okay, x, 0 and y. So anything above 0 and 1 is basically viable, right? So x is 1 and y is also 1. So this is the region of interest for this one. Anything beyond x is 1 and y is 1, right? Just putting it out there. It's not required. Now, the strange thing about actual finding marginal PDF and CDF, it's kind of a little bit different. Marginal CDFs are when you basically try to eliminate so the idea is the same, basically try to get rid of the value of x when you're trying to find out the value of y, trying to get rid of the value of y when you're trying to find the value of x. But how do you do it, right? That's the point. So when you are trying to find out fx of x, just x, okay, try eliminating y, okay? And the only way you can try eliminating y from this specific equation is when you have x and then infinity, right? If you put infinity as y, then 1 over infinity will obviously give you 0, and in that way, your entire equation is basically separated out, right? So basically, this one is 1 minus 1 over x squared, where x is greater than 1 and is 0 elsewhere. Similarly, fy of y is substituting fxy by infinity on the x side and then 1 just retaining the y. Let me see if I have the exam portion of this. Yes, so this one is the property in the CDF, under the CDF. This one is the property called, I mean, this sort of properties are available in equation 5.9a, 5.9b. Okay. Of course, this is also given, actually 5.9c as well. All right. So the marginal definition is given in the terms of cumulative distribution function. So I'm not making this up. This is exactly how you solve the problem. Okay. And similarly, you get 1 minus 1 over y squared, where y is greater than 1 and is 0 elsewhere. So please actually note down how I'm writing this stuff as well. This is exactly how you should represent a function when you actually arrive at the final value. So when I arrive at any function final value, I don't know exactly where I've done it. Like say for example, this one as well. I always mention z is greater than 0 or whatever. So the region of operation is always important to be expressed, right? So right now we already have the marginal CDFs and PDFs. But why am I trying to actually show you this problem is because let's actually try to calculate the independence, right? Is this function independent? Question mark. So what is the characteristic, or what is the rule for finding the independence? Is fxy xy is going to have to actually be fx of x times fy of y, right? So fxy we are already, so let's actually resume the LHS. LHS is basically 1 minus 1 over x squared, 1 minus 1 over y squared, and the region of operation is, let's see, I have to go back to the problem again. Oops. The region of operation is for all x greater than 1, y greater than 1. What about the RHS? Let's actually multiply fx of x, which is 1 by 1 over x squared, for x greater than 1. What about this is fx of x, and oops, and this is fy of y, right? These are the two. So you can see that LHS is equal to RHS, right? Hence, this is independent. This is an independent pair of random variables. So this is how the independence actually works. If you can isolate these two and then multiply it back together to actually get the original function, which is defined in the terms of PDF or CDF or whatever. Usually CDF, but then anyway. So that's actually the entire scope of your operation. Okay. I am going to upload the problem solution for 5110. So 5110, we can actually solve this 5110 right now as well. We still have time till 8. I hope I'm still getting recorded. But this is very easy, basically, like if you really want to solve the problem. So actually let's not keep any stones unturned, right? This is 510, right? Nothing, it's just like if you are given fxy of xy, which is exponential of minus 2x square minus y square by 2, right? And that is divided by 2 pi c. Okay, so this is the equation for all x, y. So now we are trying to find out the variance of x, the variance of y, and the covariance of x, y, right? So whenever you talk about covariance, we are talking about x and y. There is no covariance of x. There's variance of x. Covariance, co means it has to be together, right? Uh, Pay attention to the language. So, well, you can actually solve this problem in various ways. First of all, again, but I choose to basically stick to the same way that we have already discussed. Okay. So first of all, find out the expected values. After you find out the expected values, you go and find out the variance. You go and find out the After you go and find out the variance, you actually plot, or you find out the, like, it's the same. The drill is the same, right? So first of all, the sigma, right? So the solution basically is, again, you can solve this by various ways. The solution is just the same, right? Whatever equation is given out here, this is the PDF, right? So if you have to find out, if you really want to find out, right? Um, the original instructor's manual for, or the solution manual actually provides a matching solution variable. I mean, you can again do that. This involves basically matching the coefficients of every polynomial that you have in this equation, in this equation, to that of a Gaussian PDF. But then in order for you to actually do that, um, you need to basically, first of all, know what the Gaussian PDF is, and then you need to compare that with this equation to find out the difference of that, and use that to actually calculate the covariance of x and y and all the variances. So that's one way of doing it. The longer way of doing it is definitely to find out the first two. This is a PDF, so you can easily find out the marginals, right? So fx of x, what do? You basically integrate out. But then the problem for this particular problem is that the limits of integration is not given, right? So when this problem actually appeared in the exam some time back, students actually left this from this. They actually left the problem like this, okay, and dx, right? Because you don't know the limits of operation for this particular zone, right? And then fy of y is also similarly, oops, sorry, right? So from here, you can actually calculate the variance of x. Um, Actually, first of all, expected value and then variance, right? Anyway, whatever this value comes out to, right? And then you have to calculate this expected value. Similarly, variance of y, and then expected value of y as well. And then find out the covariance. So the covariance formula is basically E of xy. So E of xy needs to be found out as well, right? So those were in terms of formulas, because the limits of integration is not provided, right? So there's another way of actually tackling this problem. But the reason for this jointly Gaussian random variable, the entire point of this was that if you have a jointly Gaussian random variable provided to you, you can compare the coefficients of that specific Gaussian random variable to the variable that you have, because this is almost like looking like Gaussian, right? And then you can use those methods to basically calculate the covariance and correlation. I'm going to actually upload the solutions for this one. But then if in traditional ways of actually solving this problem is to basically go about the long way. And this is where you're going to spend most of your time. So please practice. This is probably going to be the end of my problem session out here. Thank you for attending if you are hanging out, and if you are watching it later. It's basically an amalgamation of all your homework problems as well as all your theory that has been done, all your problems that has been solved in the class today. So best of luck. I again would remind students that Dr. D will be proctoring the exam today, and he will be collecting your exams and will be, correcting them and giving them back to you whenever is possible by him. So I probably will just deliver the paper to you and leave. So if any questions and concerns, please, I'm available all throughout the day today as well as Monday. Monday, my office hours are going to be just open to basically everybody. So yeah, with that, I am going to stop the recording, and thank you so much for attending. Take care and best of luck for your exam.